In previous lecture, I discussed Euler path and Euler circuit. If a path cover all the edges, it's Euler path, and if a circuit cover all the edges, it's Euler circuit. And application of Euler path and Euler circuit. Today I'll discuss Hamilton paths and Hamilton circuit. In case of Euler path and circuit, we will visit all the edges, whereas in case of Hamilton path and circuit, we will visit all the vertex. Remember the difference. In case of Euler, we visit all the edges. In case of Hamilton, we will visit all the vertex. So definition 2, a simple path in graph G that passes through every vertex exactly once called Hamilton path. A simple circuit in graph G that passes through every vertex exactly once called Hamilton circuit. So a simple path x0, x1 till xn in the graph G equals to VE is a Hamilton path if x0 till xn are all the vertex and xi not equals to xj, 0 less than equals to I is less than j less than equals to n. And in case of simple circuit, starting and end vertex are same. Suppose it is starting from x0, then it should be end with x0. Is a Hamilton circuit if x0 to xn is a Hamilton path. If x0 to xn is a Hamilton path and at end we are adding x0, it's a Hamilton circuit. Let's see one example. Example 4. Which of this simple graph in figure have a Hamilton circuit, or if Hamilton circuit not present, a Hamilton path? These are the figure. We have G1, G2, G3. We'll check further Hamilton circuit present. If not, then Hamilton path present or not. Now check G1. In G1, we can start from A, B, C, D, E, A. Yes, we can reach to A. So Hamilton circuit present, also Hamilton path present. So for G1, both Hamilton circuit and Hamilton path present. In case of G2, no Hamilton circuit present. If we start from A, then A, B, C, D. We cannot reach to A. So no Hamilton circuit present, but Hamilton path present. We can go A, B, C, D. So there is a path from A to D. Even there is a path from D to A. So Hamilton path present but no Hamilton circuit. Now check G3. G3 Hamilton circuit is not present, as here you can see for A degree is 1, for D degree is 1, for F degree is 1. For Hamilton circuit degree should be minimum 2. So here in G2 also degree is 1, so Hamilton circuit not present. Now check Hamilton path in G3. Suppose we will start from A, B, then G, then E, then C, D. We cannot visit F, right? You can take any example. We cannot visit all the vertex. Hence Hamilton path also not present. In G3, both Hamilton circuit and Hamilton path are not present. Now condition for existence of Hamilton circuit, a graph with vertex of degree 1 cannot have Hamilton circuit. Now in G2 there is a degree 1, here in G3 degree 1. So G2, G3 cannot have Hamilton circuit because in Hamilton circuit each vertex is incident with two edges in the circuit. So for A there are two edges that use, for B two edges use, for C two edges use, means at least degree should be 2. If degree is 1, then Hamilton circuit not possible. So if vertex in the graph has degree 2, then both edges that are incident with this vertex must be part of Hamilton circuit. So for Hamilton circuit degree should be 2. If more than 2, we can ignore some edges, like here we ignore all these edges, right? When a Hamilton circuit is being constructed and this circuit has passed through a vertex, then all remaining edges incident with the vertex other than the 2 used in the circuit can be removed from consideration. In G1, we'll create a Hamilton circuit starting from A to B, B to C, C to D, D to E, E to A. So we can remove these edges, A to C, B to E and C to E. So we don't need to consider all these edges. So these edges can be removed from our consideration. We just need 2 edges for Hamilton circuit. Rest all other edges we can skip. And a Hamilton circuit cannot contain a smaller circuit within it. So there cannot be a subset Hamilton circuit inside a Hamilton circuit. So these are some points we can consider. If degree is 1, Hamilton circuit is not possible. Minimum degree should be 2. And when we are using some edges in Hamilton circuit, we can skip all other edges that were not used, and Hamilton circuit cannot contain a smaller circuit within it. Next, example 5. So that neither graph displayed in figure has a Hamilton circuit. We have two graph G and H. We'll check these two graph doesn't contain the Hamilton circuit. In G there is a vertex E having degree 1, so no Hamilton circuit. In H, A, B, D, E have degree 2, whereas C have degree 4. We need to traverse C more than once. That's why Hamilton circuit not possible. Just try. Suppose you start from A to C, C to E, E to D, D to C, C to B, B to A. So C we are visiting 2 times. In case of Hamilton circuit, every vertex should be visited exactly once. Here we are visiting 2 times. That's why Hamilton circuit doesn't possible. But here Euler circuit possible and Euler path possible, but not Hamilton circuit. Hamilton path is possible. Like suppose we'll start from A, B, then C, D, A. So there is a Hamilton path from A to A. So Hamilton path possible, but Hamilton circuit doesn't possible in case of H. So in both graph G and H, Hamilton circuit it's not possible. In G, Hamilton path possible like A, B, C, D, E. So there is a path from A to E. Next, application of Hamilton circuit. So in any area where we need to visit every vertex exactly once, like every city exactly once, each place of pipeline intersect in a utility grid, or each node in a communication network exactly once, means where we need to visit some vertex, some node exactly once, we can use the Hamilton circuit or Hamilton path. So finding a Hamilton path or circuit will be applicable for this. For example, in traveling salesman problem, where a person need to visit every city and return to its place, we can use Hamilton circuit. So the famous traveling salesman problem or TSP asks for the shortest route a traveling salesman should take to visit a set of cities. Let's see one more example where I will discuss both Euler path, Euler circuit and Hamilton path and Hamilton circuit. Example 6. Which of the simple graph in figure have Hamilton circuit, or if not a Hamilton path, a Euler circuit, or if not an Euler path? These are the graph. There are 4 graphs. We need to check in each graph for the Euler path, Euler circuit, Hamilton path and Hamilton circuit can be possible or not. Now check G1 graph. In G1 graph, A degree is 2, B degree is 4, C degree is 3, D degree is 2, E degree is 4, F degree is 3. So Euler path is possible. We can start from F and end at C, or we can start from C and end at F. So for G1, Euler path is possible, but Euler circuit doesn't exist. For Euler circuit, every vertex degree should be even. Here there are 2 vertices whose degree are odd. So Euler circuit doesn't exist, but Euler path exists. Suppose we'll start from A, we can visit B, C, D, E, F. Yes, Hamilton path exists. Even Hamilton circuit also exists. In case of Hamilton path and Hamilton circuit, we need to visit all the vertex, whereas in case of Euler path and Euler circuit, we need to visit all the edges. So here Euler circuit doesn't exist, but Hamilton path and Hamilton circuit exist. Next, graph 2. In graph 2, all vertex degree is even. Euler path, Euler circuit both exist. Suppose you will start from A, E, C, B, then E, D, A. Euler circuit exists, even Euler path exists. Now Hamilton path, suppose you will start from D, A, E, C, B. Hamilton path exists. For Hamilton circuit, then we are visiting this E 2 times, then we are going to D. Okay. So that is not possible. We will visit every vertex exactly once. So Hamilton circuit doesn't exist. In G2, Euler path, Euler circuit, Hamilton path exists but not Hamilton circuit. Next check G3. In G3 here degree is 2, degree 4, degree 2, degree 4, here degree 2, degree 2. So all vertex degree is even, Euler circuit and Euler path exist. Next check Hamilton path and Hamilton circuit. Suppose we'll start from D, A, then E, C, F. We need to visit A again. That is not possible. So Hamilton path doesn't exist, even Hamilton circuit doesn't exist. We cannot visit all the vertex exactly once. So both Hamilton path and Hamilton circuit doesn't exist for G3. Next check G4. First I will find degree of all vertices. E degree is 3, D degree is 2, 3, 2, 3, here 3, here 2. There are 4 vertices whose degree is odd. So for Euler path, there should be exactly 2 vertices whose degree is odd, that we can start from one vertex and we can end at other vertex. All degree are not even, so Euler circuit doesn't exist. So for G4, both Euler path and Euler circuit doesn't exist. Now check Hamilton path. Suppose we'll start from D, D, E, F, C, B, G, A. Yes, Hamilton path exists but not Hamilton circuit. In today's lecture, I discussed Hamilton path, Hamilton circuit with example and applications. In case of Euler path and Euler circuit, we are visiting all the edges exactly once, and in case of Hamilton path and Hamilton circuit, we are visiting all the vertex exactly once. If this lecture is helpful for you, please like, share and subscribe. Thank you.